Welcome again to Physics 142 Online. Today I'd like to give you an introduction to a really interesting and very useful physical phenomenon called the Doppler Effect. And in its simplest terms, the Doppler Effect is simply the experimental measurement, the experimental observation that the frequency of a source of waves is affected by both the motion of the source and the motion of an observer. And we're going to illustrate that, and we're also going to work out mathematically how we can predict what those frequency changes are. But before I do that, I'll just mention that the Doppler effect is the basis for our knowledge that the universe is expanding. It's also one of the ways that we measure the fetal heart rate in a pregnant woman, and it's also the way that your friendly police officer knows that you've exceeded the speed limit. And so these are effects that touch us in our daily lives and have profound significance in areas of science, especially in astronomy. So this first picture illustrates the idea of waves being emitted at a regular frequency from a source S. And the picture corresponds to what you might see if you were looking overhead and someone was dropping a rock repeatedly in a pond. You would see ripples spread outward in circular shapes from the source. The Doppler effect in most of the problems that we will do will apply to sound waves. And so actually you should think of the sound waves being emitted on the surfaces of spheres that are expanding outward in 3 dimensions. But most of the pictures that we draw will just give the 2-dimensional approach. So the waves themselves are moving outward in all directions with a speed v, and we want to consider what observers A and B will notice as we consider the motion of the source in one direction or the other, and as we consider the motion of A and B themselves as our example observers. But first, let me illustrate how this works using a very simple computer demonstration. Okay, in just a moment, what we're going to see is a simulation of what would happen for waves emitted by a source that's moving, in this case, moving to the right. Notice what happens. These circular waves are emitted, but since the source is moving, at each time the wave is emitted, the source has moved a little bit to the right. And so the circles no longer are concentric. And as a result of that, the wave fronts, which are the surfaces of the waves, they might correspond, for example, to the troughs or to the crests of adjacent waves. Those wave fronts get squashed closer together on the right-hand side in the direction in which the source is moving, and on the left-hand side they get further apart. And so what we see is that the wavelength, the distance between identical points on the wave front, changes. It's shorter in the direction of motion, and it's longer in the direction away from the motion. Let's just look at that one more time. So the source is catching up to the waves that have already been emitted, and that's why the wavelength is shorter. So the basic idea in this effect, as you'll see in the still picture here, is that the change in those wavelengths as the source moves toward observer B is going to affect the frequency. The wave's speed hasn't changed, the wavelength has gotten shorter, and so the frequency should increase. And that's summarized here underneath observer B. The wave speed v prime stays the same, that hasn't changed. The wavelength, lambda prime, measured by observer B, is shorter, as we've discussed. And f prime is therefore larger, because the wave velocity, the frequency, and the wavelength are related. So since v hasn't changed for observer B, but lambda has gone down, the frequency must go up. And conversely, observer A who is watching the source move away, again, observes the wave speed to be the same. The motion of the source has not changed the speed of the waves, but has observed that the wavelength is larger, and therefore the frequency that observer A measures will be smaller. Now we'd like to do something more than just be content with a qualitative description, and that is to go on to quantify this. But before we do that, let's consider the other possible case. The other possible case is due to the motion of one of the observers, A or B. And in this next slide, what we'll see is a case where both A and B are moving to the right with a speed v0, but the source is stationary. So we see the source emitting these waves outward in all directions uniformly, A moving toward, B moving away. And before we can analyze this, once again, I'm going to show you a short computer simulation of this effect. What's going to happen in this simulation is that the source at the center will send out waves and will remain stationary, while the observer on the left will move toward the source. Initially there will be no motion, but then you'll notice the observer begin moving toward the source. And we have to ask ourselves, what will this observer notice different as he or she moves toward the source? You can see right there, the wavelengths are not changing, and here the observer is moving away from the source. The wavelengths haven't changed. If the observer were carrying a meter stick, then he or she would measure exactly the same wavelength that they had measured in the absence of any motion. So it's not the wavelength changing here, and we can see that because the waves don't bunch up or spread apart. But what's different in this case is that the observer will encounter the waves at a different rate. In other words, to this observer, those waves will appear to be traveling faster as the observer is moving toward the source, and will appear to be moving slower as the observer is moving away from the source. See if you can see that now. All right, here goes the observer. Those waves appear to be moving faster. Then after passing the source, those waves appear to be moving slower to the observer. And that is the basis for the Doppler effect due to a moving observer. So what that video clip showed us was that for observer A moving toward the source, the wave velocity increases. So V prime is greater than what V is if the observer is not moving. The wavelength stays the same, but therefore the frequency increases, because if the velocity is going up and the wavelength stays the same, then the frequency must go up, according to our equation V equals F lambda. And just the opposite happens for an observer B moving away. When the observer is moving away, the wave speed is decreased by the amount of the observer's motion. So V prime is less than V. Lambda prime is equal to lambda. The wavelength doesn't change, but now in this case the frequency goes down. So now that we've seen an effect due to the source and an effect on the frequency due to the observer, can we try to quantify our understanding of it so that we can calculate the shift in the frequency? And that's what the Doppler effect is really all about. Sometimes we talk about the Doppler shift, and by that we mean the shift in the frequency measured by the observer compared to what would have been measured if there were no motion. So in this situation, let's re-examine the source moving toward the observer. The source here at point P initially is moving to the right toward observer B. The various speeds and frequencies are labeled here in the box, and what we want to consider that at the initial time the source is at P, and then a short time delta t later the source is at Q. And so that source in that time has traveled a distance equal to the speed of the source times the time delta t. And that's what we're going to use to understand quantitatively what's happening. Now we said here that the wavelength in the direction of motion is shorter. How do we calculate that? Well, this new wavelength would be the distance from Q to C divided by the number of waves that there are between Q and C. All right, now what is this distance between Q and C? Well, it's the distance that the waves travel in a time delta t minus the distance traveled by the source in the time delta t. Right? And so if the source were at rest, then the total distance the waves would travel would simply be v delta t. Right? But since the source is moving, then effectively the distance they've traveled away from the source is just the distance qc, and that is v delta t minus v source delta t. Remember, v source delta t is this distance here. The delta t is not in the figure, unfortunately. While the distance between P and C, the distance that the waves travel, is v delta t. So if we subtract those, we get this distance from Q to C. Now what about the number of waves that were emitted during that time? Well, the waves that were emitted during that time are equal to the frequency times the time, right? Frequency is number of waves per unit time. Delta t is the time interval. And so the distance divided by the number of waves is the distance per wave, otherwise known as the wavelength. So when we look at this expression, we see that the delta t is common to all terms, and therefore it cancels out. So this lambda prime, which is the shortened wavelength that observer B will measure, is v minus v source over f. Remember what these represent. V is the speed of sound, or the speed of the wave. V sub s is the speed of the source, and f is the frequency of the source that would be measured by the source, by someone with the source. So what's left is for us to calculate the shifted frequency. And what we think of now is all of these quantities measured by observer B. B would measure a v prime, an f prime, and a lambda prime. And we've just calculated the lambda prime. So let's use this equation to calculate the Doppler shifted frequency f prime. F prime is v prime over lambda prime. Well, we know that the speed of sound hasn't changed for this observer, so v prime is still just v, but now we know that lambda prime is v minus vs over f. And so we put that into the denominator. V over v minus vs divided by f. Well, the f in the denominator comes up to the numerator, and we get that f prime is equal to f times this ratio, v over v minus vs. So let's keep that for future reference in the blue box at the right. Notice that in this case, since the wavelength went down, that means that the frequency went up. And that's the kind of thing you would hear if you were listening to a train whistle on a train moving towards you at the station. You would hear a sound at a higher frequency or a higher pitch than you would have heard if the train were not moving. The same effect applies to an observer who is watching the source move away. The only difference here is that the wavelength appears to increase rather than decrease. And so the only thing we have to do, if I go back for a moment to the previous slide, the only thing we have to do is take the minus sign and change it into a plus sign. Because what we're finding is a new wavelength that's longer than the original wavelength. So this lambda prime becomes v plus vs over f, and I will quickly speed through this because the same result is obtained for the Doppler shifted frequency f prime, except the sign has changed. So it's v over v plus vs. So if we compare, I'll go back one slide. Well, the previous slide simply said that f prime was v over v minus vs times the original frequency. So we'll put those together in a single equation in just a minute. First, though, let's consider the other situation. In this case, now the source is stationary, but the observer is moving. So we're halfway there. What we want to do is look at how the new velocity, the new wave speed, affects the measured frequency. Remember we said that when the source is stationary and the observer is moving, what happens is the wave speed increases. So for observer A moving toward the source, the wave speed is v plus v0. While for the observer moving away, and therefore moving away from the waves are chasing, but the B is moving away, so the net speed is smaller. V prime over here is v minus v0. As a result of this, v prime being greater than v, the wavelength is the same. Then for A, the frequency goes up, while for B, the frequency goes down. So we're going to do the same kind of calculation for A, and then for B. We use v prime equals f prime times lambda prime. So we solve for v prime, the frequency now that A would measure. That's v prime over lambda prime. Lambda doesn't change. Lambda is the same as what it would be in the absence of motion, but the wave speed has changed. So now we use v plus v0. We put that into place. And then we do a little bit of algebra. We can see that lambda in the denominator is the same as the original wave speed over the original frequency, v over f. And then that f comes up to the numerator. So now we have an expression f prime is v plus vo, the observer speed, over the wave speed times the frequency. Nice compact formula that shows us if we know the observer velocity and we know the wave velocity, we can get the frequency measured by the observer. For observer B, you guessed it, it's the same basic idea, except since the wave speed has decreased, the v plus v0 becomes v minus v0. Once again, we do the same algebra, and we come out with this result here. Now, let me just stop for a moment and summarize. What do these equations in the boxes mean? What they mean is that the original frequency that you would measure if you were at the source is f. That's the frequency of the source. V is the speed of the wave in air. That's the speed that someone at the source would measure. Now, if there's no motion involved, that would be the wave speed. VO, in this case, is the speed of the observer. In the previous case, we had an equation that looked like this, except it had the speed of the source involved. Okay, so that's what these equations are useful for. But they're so similar, particularly when we're just talking about the direction of the motion, that it makes sense to put them together into a single, unified equation. So let's do that. What if both the source and the observer are moving? It's pretty easy to see what happens. So let's review. The Doppler shift for the moving source. All right? We had two equations, but I'm putting them into one right here, writing that as v over v minus or plus vs times the frequency. Why did I choose it that way? Well, what I did, the original case I considered was when the source was moving toward the observer, and that produced the minus sign. So the upper sign here corresponds to motion of the source toward the observer, and that makes the frequency go up. The lower sign, in this case the plus, that's for motion away from the observer, right? And that makes the frequency go down because the denominator gets larger. So this summarizes both directions of motion in a single equation. But now we've also got the moving observer. So what if the source is stationary and the observer is moving? Here is the combined equation that includes the case both for motion of the observer toward the source, that would be the upper sign right here, and for motion of the observer away from the source, which is the lower sign, the minus sign. Okay, now we've got two equations, but can we do better? Can we combine these into one? And the answer is yes, because the two effects, motion of the source and motion of the observer, they're independent of each other. So I can consider motion of the source in the upper equation, and then take the result, the resulting equation for f prime, and plug it in for f in the second equation, and see what the motion of the observer does to it. And so we see that these two effects simply multiply. If I took f prime in the top equation, plugged it in for f in the bottom equation, I would get the net result of both effects. And what would happen is, you can sort of see what would happen, the v in the numerator and denominator would cancel, and I would be left with this equation here, which looks kind of intimidating because of the plus and minus signs, but is really not too difficult. All we have to remember is the observer velocities in the numerator, the source velocities in the denominator, and we have to remember that the upper signs are used for relative motion toward either the source moving toward the observer or the observer moving toward the source, and the lower signs are for relative motion away from. So that is a fairly brief introduction to the physics and the quantitative description of the Doppler effect for this special case where the observer and the source move along the same direction toward one another. It can get really complicated in a hurry if they move in different directions, but if they're essentially moving in a one-dimensional system, this is the correct equation. And we will work out some interesting examples in class.